Okay, now it's going to be recorded. Please bear with us if any technical issues arrive. If Zoom goes down for any reason, we'll switch to presenting via teleconference line. And if that happens, I will immediately send out an email to all panelists and attendees with information on how to access that teleconference line. If you have any technical difficulties during this, please email us at news@adu.org or drop something into the chat. And so once again, this is meant to represent sort of a roundtable experience, a personal discussion with the panelists. So don't feel like it's so formal. If you have a question, you can drop it into the chat. You could raise your hand and ask to just turn on your mic and start talking after the panelists give their presentations. And Mike Buckley here from Johns Hopkins is going to moderate that discussion. So with that, I'm going to turn it over to Mike to give you a little more information, introduce all of his panelists, and get started.
All right, this is great. Thanks, Liza, and welcome everybody. We're just excited to have the opportunity to tell you all about this amazing concept, this study for an interstellar probe. Just some basic background on this too. This is a study that's about 4 years in the making, but a concept that's decades in the making. And a team led by the Johns Hopkins Applied Physics Laboratory recently completed the most in-depth study on such an interstellar probe concept to date. So we have a few of those team members here that again just want to be able to give you some background on it and to discuss it. The report is now available online, nearly 500 pages. Like I said, this is detailed, it's in depth. It's available at http, of course, / the interstellarprobe.jhuapl.edu. And those links will also be made available in the chat. So I'm going to let the team members introduce themselves, and then there's a short presentation that Ralph McNutt will give, and then we'll get into the Q&A. So there's enough people on here. If you just want to put something in the chat, I'm happy to read it. In the reactions, if you want to raise your hand, we'll get to it as we go around the discussion, but we'll leave it that way. But I'll turn it over to the team to introduce themselves and their roles in the mission.
Well, good afternoon. I'm Ralph McNutt. I'm the principal investigator on this study. And again, as Mike said, we've been at this now since June of 2018. It's a report going into the heliophysics division to help to inform the next solar and space physics decadal survey of what one might be able to do with an interstellar probe mission. Again, this is something that's been talked about for about the last 60 years, and this is really a deep dive into the engineering.
Hi there, I'm Pontus Brandt, so I'm the lead project scientist. We have about 500 people or more in terms of supporters and people that have signed up, both engineers and scientists. We have over about 120 active, very active scientists that we now have divided up into 8 working groups to handle all of this really, really rich science just by going through our magnetic bubble that harbors the entire solar system and beyond into the interstellar medium. So I'm sort of the lead project scientist to organize all of that. And to my right here, I have Elena, and she is our eminent lead for heliophysics. Elena.
Thank you, Pontus. My name is Elena Provornikova, and as Pontus said, I'm a lead for heliophysics science in this mission, and I have been working with lots of scientists, and we got an impressive list of science questions that we can answer with this mission.
Hi, my name is Alice Cocoros. I'm the payload systems lead. So my position is mainly to serve as a gap bridger between the engineering team and the practicality of this mission, which it is pretty practical actually, and the scientists who have beautiful, lovely dreams that we want to realize.
All right, this is great. Thank you all for the introduction. So why don't we just move over, if Alice, again, if you could run the presentation. Ralph, you can take over and we'll go through this overview. Okay,
very good. So this is a short summary of what we've been up to. And Alice, there we go. So basically this gives you a little bit of an idea of where all of this has landed. Of course, the idea here is to get away from the sun and to get out into the local interstellar medium. but really doing science all the way along the way with an advanced payload and being able to do comparisons of what's actually going on across almost 5 solar cycles. The overall mission is divided up into 3 phases: a heliosphere phase, out to the termination shock, a heliosheath phase, through the heliosheath, a region of space that only Voyagers 1 and 2 have been through, and then finally an interstellar phase to be able to go at least twice as far and twice as fast as Voyager 1 with a brand new payload. Next slide, please. So here's an idea of what the spacecraft looks like. It's been described as Voyager on steroids, and there's a reason for that. The main thing that you have to do is to be able to get the data back down from very large distances. So this is actually looking away from the Earth. So this is a 5-meter diameter high gain antenna with 2 next generation RTGs for power, a baseline payload for heliophysics of 10 instruments divided into charged particles, fields and waves, energetic neutral atom imaging, looking at dust, neutrals, and looking in the ultraviolet. About 90 kilograms, about 90 watts of power. Overall, a spacecraft that would come in with a mass of about 860 kilograms, not too different from the overall spacecraft mass and the overall payload mass of the Voyagers. Next, please. This gives you a little bit of an idea of what we've been looking at for a package on all this. If one were to launch about the year 2036, that would enable us to go into the forward hemisphere of the heliosphere. That is the hemisphere looking on the side of the incoming interstellar flow. This has actually been designed with a technology launch horizon so that we could be ready to launch by the January of 2030. The launch opportunities that are possible are every 13 months because all of the options include going by Jupiter for a close Jupiter gravity assist in order to be able to get our speed up. Again, I mentioned the 2 next-gen RTGs. Communication system has been designed separately to be able to get data back from as far away as 1,000 astronomical units. And that's with a 5-meter antenna and using X-band for communications. And a lot of people say, well, why not Ka or optical? And the reason is spacecraft pointing. And pointing, it turns out, is one of the things that we got involved with in a very detailed way with the overall system design. And X-band really is the way to go to be able to assure that one can design a mission which will last for 50 years by design and be able to transmit data back from that far away. And I just noticed with the graphic here down at the bottom, one of the things that we've talked about is by designing in basically a generational approach where that once every 10 years there would be a turnover in terms of both the scientists as well as the engineers and as well as the managers for the people running the mission. Because by design, having something that's going to last for 50 years and doing that reliably is going to call upon having an apprenticeship program and an ongoing rotation of the people that would be doing the job. Notionally, we've been talking about using a space launch system, Block 2 cargo version. We've been working with colleagues at Marshall Space Flight Center now for about the last 3 years. The basic design is pretty much agnostic to what exactly that the launch vehicle is, as long as it's one of the super heavy lift launch vehicle classes, which is where that the SLS is. Marshall has been so kind as to be able to provide detailed data on performance. And so we've been working a lot with them on all of this. Basically, under the fairing on the SLS Block 2 cargo, we would have a 3rd stage, it's a Centaur upper stage, a 4th stage, it's a Star 48 BV solid, and then finally the spacecraft. Next, please, Alice. And this just, again, this is a short movie. This is put together by APL and by Marshall to give you an idea of what this might look like. Again, notionally a launch maybe around the year 2036 or so on the SLS Block 2 cargo. with what's called the long fairing in order to be able to put the third and fourth stages as well as the spacecraft there. This is, of course, going up on the solids along with the RS-25 engines firing on the core stage for the SLS, heading us up toward a parking orbit. Stages coming off, the core stage taking over. As we head on up, start turning over, staging to the exploration upper stage with the 4 RL-10 engines. And of course, this is the same basic design for going to the moon with people on the Artemis program, but in this case, we would be going into a low Earth orbit about 100 nautical miles up to be able to phase over to do a burn to get into, to head toward Jupiter. With the Centaur firing up after the exploration upper stage has used all of its power, and then with the Star 48 BV firing up, launch energy something like twice that of New Horizons. We would be crossing the orbit of the moon something like about 6.5 hours after the launch at a tremendous speed leaving the Earth. The spacecraft is a spinner. This is showing you reorienting the spacecraft to point the high gain antenna back toward the Earth. As we go past and out of the Earth-Moon system, starting to deploy the magnetometer boom, which is a critical instrument for doing the measurements into the nearby interstellar medium. We've also been talking with colleagues. We'd have 4 50-meter long wire antennas in order to pick up a noise in the interstellar medium. 7 months to Jupiter, a very fast flyout speed, crossing the orbits of Saturn, and finally Uranus and Neptune, and then out to the orbit of Pluto, across the termination shock, maybe in the order of 80 to 90 AU, then into the heliosheath, across the heliopause, and into the nearby interstellar medium. With the design that we've got here, we'd be able to reach at least 375 astronomical units in 50 years. And of course, it's all about exploration. It's all about the science. And that's a summary of the mission. And again, Mike has given you the website, and I think it's probably in the chat as well, for where the final report is. That was just released last night, about 496 pages. And we're looking forward to getting comments back from the entire community and all of the potential stakeholders, from scientists to policymakers and others. So thank you for your time and your attention.
Okay, so with that, the floor is open. So we'll look for if there's something you want to put in the chat, or simply, if you want to raise your hand on the screen, or do the a hand raising reaction. We'll just call on you and we'll get the conversation going. So I see Jonathan's got a question. O'Callaghan.
Hey, yeah, I've got a few questions. I'll just start with a couple. Can I ask what's new in the study now compared to, say, a couple of years ago when kind of the proposal first came up? Like, what has this study kind of solidified in terms of how the mission would work? And could you also tell me, is it with regards to kind of decadal surveys and NASA involvement, where things currently stand there? Is there any, is this still considered as part of the heliophysics decadal survey, if I'm getting that one right? Or is it still, are you looking down those routes to kind of get support in that way? Thank you.
I'm going to assume that's for me, Jonathan. So basically what we've been doing is we've been trying to fill out some of the details of the concept that as it stood a couple of years ago. Alice and the rest of the team and a whole host of people, about 80 people, have been working on trying to hone the science questions, trying to really take a close look at the sorts of instrumentation that are out there that would enable you to address those questions, kind of what these things would weigh, how much power that they would need, to try to put together a design that really would close. I mean, we've been looking at really putting together a menu from which that the rest of the science community could place an order. We've also been trying to worry about what this sort of a mission would cost. There's a chapter in the report that's out there talking about the cost. We think we've done a good job on that. One of the issues that people have talked about a lot is trying to use the solar Oberth maneuver to do a powered maneuver close to the sun in order to try to get out of the solar system fast. no one has ever really done a detailed design study of looking at the thermal conditions of how to make that work. And so one of the things that we've really been concentrating on this last year is taking a very close look at that. Again, all documented in the report. What we've been able to conclude is that while one could go very close to the sun, one has to worry about what kind of a thermal shield mass one would have to carry along. And basically it comes out to being close to a dead wash on the kind of the speed that you can get out of the solar system. And so the simplest thing, doing a direct descent from the Earth and then on out, is probably going to give you about the same performance as you would get from trying to go in close to the sun, which would cost you more because you've got to do a lot more research on trying to deal with the thermal environment. With respect to the decadal survey, that's for solar and space physics. This is an exercise that is going to be starting up. I think it has started up. Of course, this is run by the national academies in the US, and it's done indeed once a decade to decide, well, basically to have the community decide and put it in writing about what sort of exploration program that there should be over the next 10 years. So this report was really done as one part of an input to that study. There will be several panels probably that will be put together for the decadal. I don't know exactly what the plan is this year as compared to what was done 10 years ago. Likely I think the current schedule is to get the decadal up and running within the early years of 2022. And then hopefully by the end of 2023 or 2024, that panel of people will be able to come back with recommendations on what the heliophysics plan should look like for the next 10 years. And so this particular study was done as input to be able to try to help inform them of what one could and could not do with an interstellar probe. Again, this is something that's been on the books at least since 1960, a myriad of studies. And but this is the deepest dive in terms of the engineering, and all the science has been updated. Again, as Pontus mentioned, we've had almost 100 people really working on this, a lot of volunteers, 1,000 people have looked at the webinars, 500 people on the listserv. And so we've been reaching out to people literally around the world as well as around the country to get the word out on what a mission like this might look like. And it's a question of whether that people will see that this would be a good thing to do. So it's offered up for to move to the next stage for the judgment of the Decadal Survey Committee.
Okay, great. Thank you, Ralph.
Anybody else want to chime in, guys?
I just emphasize that I feel
sure,
like. Oh, you go ahead, Pontus.
And they all jumped in.
And we all jump in. Sure, I can jump in on, yes, this is for the Solar and Space Physics Decadal Survey, of course, and the mission is anchored in heliophysics. It's been a mission, it is a mission to go through the boundaries of the heliosphere, this vast magnetic bubble that encases the entire solar system, as I said. And all in all, over those, to go back to Jonathan's question here, over these 4 years working with this entire community, I think we sort of are coming in and we're focusing in on the real reasons for existence for a mission like this. And it has to do with the evolution, not only of the solar system, but of the heliosphere and the solar system together. Because as you remember, 4.6 billion years ago, this solar system started to take form, and with it, this magnetic bubble as well, which shields us from all the dust and plasma that we plow through on our journey through the galaxy. So really have this interstellar probe going from the inside and out to understand the physical mechanisms will allow us to not only understand the current state, but also understand where we come from and how this has affected the evolution and where we're going next. Because not many people know, but we are about to exit and leave our local interstellar cloud that this heliosphere has been plowing through for the last 60,000 years. And we're entering a completely new region. We have no clue what's going to take take place and what's going to happen to the heliosphere. It could be, a huge heliosphere spanning the heliopause out to, I don't know, 600 AU. It could be a very compressed heliosphere. We just don't know. So that's sort of the reasons for existence and getting out there to understand it. Alice, your turn.
Thanks, Pontus. On the other side of things, the more practical side, I feel like what our study has done as a member of the engineering team is taken these dreams that the scientists have and put engineering behind them to support what we can and cannot do, as Ralph alluded to. So I think one of the most important pieces of the work we've done has been to look at what is possible in terms of instrumentation and the spacecraft itself, trajectory, all of those different engineering pieces of it, and then reevaluate what is the science that we can do, and come to the conclusion that with near-term technologies that won't need a whole lot of infusement or development, we can accomplish all the science we want to do with this mission concept, which is pretty exciting.
Maybe Elena, you want to jump in and talk about the heliophysics?
Yeah, sorry. Absolutely, yeah. And just to add, I guess, to what Alice was saying, that over these years, we worked with scientists in our community to, to get this set of science questions that cover all the mysteries that we have today about our heliosphere, about how the heliosphere interacts with the interstellar medium, what is outside. And we got this set of questions, and then our task was to come up with the requirements, what kind of measurements and with what precision and what resolution we have to make to make sure that we answer all the science. So that was the main progress, which is in the report.
Thank you. Well, Jonathan, way to spark it. Way to get that going. Some good questions to get the conversation going. I noticed that some people have come in late, so I'll mention there's different ways that we're going to take questions for this. Again, this is all like we're sitting around the table. So if you have a question, you want to raise your hand on the screen, that's cool. You want to put it in the chat. That way we can get to that. I can read it if you don't want me to do that as well. So we can leave it this way. In fact, so here's one in the chat from Matthew Walter. So it just says, thank you for an exciting project. Can you explain imaging possibilities that might be possible in the interstellar medium?
All right, that would be
Pontus, Elena.
Yeah, I can take this one, and then Pontus will talk more about ENAs. So Interstellar Probe will have two main imaging capabilities: the measuring energetic neutral atoms. Those are hydrogen atoms that form from the important process, which is charge exchange process. And so those atoms form everywhere in the heliosphere boundary, inside the heliosphere, even outside in the interstellar medium. So we will have a camera that will measure, they will make sky maps of those ENAs, energetic neutral atoms. And we will be really able to see how those maps change as we go with the distance far away from the sun, how those maps change. This will help us to understand where those ENAs come from, where the sources are, and what it tells us about the global structure of the heliosphere. And in other imaging capabilities is to measure the emission from the very low energy hydrogen atoms. Those are interstellar hydrogen atoms that come from the interstellar space, and they come into the heliosphere, also go through the charge exchange process. And we're going to measure the line profile of that emission, and that will tell us about different processes that hydrogen undergo at the heliosphere boundary, inside the heliosphere, outside. And again, this all links together into the heliosphere.
I can jump in with just one quick sort of takeaway message and comment here for the ENA imaging part. At least this will really be the first time that we get outside of our habitable magnetic bubble to turn back and take a picture of our home, of this entire structure that spans, you know, several hundred AU in one direction and much more in the other direction, we think in the tailward direction. That's the takeaway message for ENA imaging and partly also for UV imaging.
Okay, great question. So it looks like Jonathan's got his hand raised again. So Jonathan, go ahead.
Yeah, regarding the launch vehicle for the mission, you mentioned about using obviously SLS Block 2. Have you considered other proposals? Obviously, Starship being one that by 2030s might be operational if it does come to pass. Given the added metric ton lifting capability of that rocket, would you consider using that for the mission? Would that change the mission profile at all? And on the mission trajectory, I think the original proposal had maybe a sun flyby included as well. Maybe I got that wrong. But was that still considered going via the Jupiter then the sun, or was that something that was changed in the mission proposal? Thanks.
So, yeah, so why don't I grab those? Let me take them in opposite order. So the going by the sun, that was the so-called solar Oberth maneuver after Hermann Oberth, who came up with this idea of rapid escape from the solar system back in 1929. And this is the one that we took a look at about the thermal issues, because the joke always is, well, you know, all you have to do is go at night, except of course that doesn't work. So that was the one that we studied. And like I say, we came to the conclusion that you probably are not going to gain that much of an advantage from that because of the amount of mass in the solar shield that you'd have to carry with you, because it tends to actually to slow you back down. With respect to the other launch vehicles, Starship, yes. New Glenn, yes. Anything anybody else wants to throw on the table, yes. I mean, basically right now, the technical specs are to be able to take a spacecraft with a mass of about 860 kilograms, like I say, very close to the mass of Voyager. And from a technical point of view, being able to get up to what's called the C3 of about 300 kilometers squared per second squared, which is basically a measure of the asymptotic escape energy from away from the Earth after that you've actually escaped the Earth's gravitational field. To date, the fastest thing, most energetic thing we've launched from the Earth was New Horizons. It had a C3 of about 156. Solar Probe was a close runner-up with a C3 of about 154. And we're talking about doubling it to something on the order of 300 or a bit more than that. And really the interesting trait, I think, is that it turns out that if you want to get people to the moon, you need something that is on the order of the SLS or the Ares 5 or the old Soviet N1 or the Saturn 5. Basically this class of super heavy launch vehicles. Starship is in that class. I think from what I've seen of the specs, New Glenn is planned to be in that class. The reason that we seized on SLS, or the main reason really, is that the data were available for being able to look at what kind of performance that we might get as a function of mass. And again, the people at Marshall have been incredibly helpful with that. We've also talked with people at Boeing. We've talked with people at ULA. We've talked with some of the people at Arianespace. We've talked with some of the others with the other companies. You know, for various reasons, people don't necessarily want to put all their cards on the table, and a lot of these vehicles are still under development, and people are still worrying about what kind of performance that you can get. But C3 of 300 for a spacecraft at 860, take anything we could get, and you know, that's exactly the sort of thing that one should take a look at as these other designs mature. Hope that answers your question.
Okay, looking around. I can see, you know, in the meantime, I'm curious about something. I want to bring up a point too, that the completion of the study from APL, right, means no assumption that APL would manage or expects to manage such a mission, right? There would be an entire process before a mission like this even becomes real. This concept you explained, the role would have to play in the decadal surveys, and then if they even had to be proposed or something along those lines. But if you were in the position, right, to see this mission through. I was curious for something longevity. You know, Ralph, you had mentioned in one of your slides about the generational differences and, you know, incorporating different teams. What it's like to be putting a mission together that one, you might not see the end of, or, you know, to be on the tail end of something, knowing that already you're going to have to hand it off to another generation to take over, you know, before it gets to its point of what you wanted to design it to do. So I think I'd imagine all four of you have a different take on that.
Who do you want to jump in first, Mike?
You can pick whoever's feeling it most.
Well, okay, so I'll go ahead and jump in, and then I'll try to jump back out soon before I have a revolt by the other people here in the room. Yeah, you know, suppose this thing launched in 2036, and you know, got to you know, nominal end of mission in 2086. So let's see, that puts me at about 130 years old. So I don't think I'm gonna worry too much about being there for that particular milestone. You know, you do these projects, and it really is a question that you need to be thinking about handing them off. I mean, there are long time scales that are involved. I tell new people in the field, you know, if you're into instant gratification, do not get involved with space exploration, because it just simply doesn't work that way. But, you know, I've had all of my opportunities to be able to sort of see the things that got us all started. I was actually a graduate student, and I got to see Voyager 1 launched, and I'm still a member of the Voyager science team. And we're kind of getting to the end of that one, but that doesn't mean that people shouldn't be paying it forward all the time. And so, you know, I see this as this is the way that science progresses, is that you do pay it forward. You do try to, you know, keep handing things down to those next generations and setting them up for success. And, you know, so far I've been able to convince many of my younger colleagues that this really is the next step, and this is something that makes sense. And with that, Elena, I'm going to put you on the spot and let you pick up the conversation.
Okay, thank you, Ralph. So I've been in the field of the outer heliosphere for about more than 10 years now. And when I was a graduate student, I heard about Interstellar Probe concept, because that's not a new idea. It's been around for quite a while, and I was always interested. I was always following. And now it was during last few years, it was a fantastic opportunity for me to be a part of this study. And I'm very interested in, I hope it will go forward very much. And I'm very interested to be involved down the road, and, you know, to learn from Ralph, to learn from Pontus, to learn from everybody in the team, and, you know, pass this knowledge along to next generation of bright students and postdocs, and see their success in this mission. So Alice, anything to add?
I have lots of things to add as usual, but tell me to shut up. But so one big aspect here that comes to mind is it's not only, you know, 50 years, we believe. I mean, look at the Voyagers. Voyager's not outlived its design lifetime by a factor of 10. For just looking at the spacecraft system we have today, it is very likely that we would survive even out to 1000 AU, which is 120 years or so from launch. So, you know, just think about your grandkids and where they will be and what we should tell them already today. Ralph already mentioned this sort of pragmatic new generation and transitions, and it's happening actually already today. So I'm leading a few instruments also on the JUICE mission, which is the Jupiter Ice and Moon Explorer on the ESA side, and already there from the get-go, it's sort of a long mission. We had to plan for that, but it's at much smaller scale. We're doing it on a much larger scale on the New Horizons mission. You know, extended mission proposal is going on, so that is baked into the plan in reality, and we can't sweep it under the rug. Meaning it does cost money. You gotta bring the people on board and have them next to you early on. I'm going to end on the note that, there are two things that really inspire people. One is obvious, to boldly go where no one has gone before. But the other aspect is this beauty of a long mission where you do it for your future generations, because inevitably that is where space exploration is going to take us. We do this for the future generations.
That was great. Thank you, guys. I see we do have a question. Rich Stone has his hand up. So Rich.
I think I'm unmuted now. Thanks. Two questions. The first is regarding the Interstellar Mapping and Acceleration Probe mission, which I think is set to launch in 2025. Is like the scientific objectives of your mission, do they depend on the outcome of that mission? Do you have to wait to see what that mission finds first? So I think I would start with that question.
Everybody's looking at me.
I can take it if you want.
No, let me start quickly. I feel I'm talking too much, but so we both have the IDEX mission, and we also have the IMAP mission coming up. And basically, they're doing a great job on that team, and IMAP is also an APL mission, of course. But to me, that's really the, how should I say, the guide or the map of where we need to go. As everybody knows, it sits at 1 AU. We're trying to image this vast structure from the inside. And recently, there was a 3D map released by the IBEX team, which is amazing. It's what we think is the structure of the bubble. But basically, I think the takeaway message is it's the map of where we need to go. Do we rely on it? That's a strong word, but there is so much science that we can refine, and the power of an interstellar probe is not really the imaging, it's the fact that we're going there. And we already know from the IBEX and IMAP missions, all these questions that have popped up because of the patterns in the sky. We have no clue what they are. And that's the reason to me. Elena, sorry.
And just to add to what Pontus said already, it's probably you're familiar with this, with the IDEX mission that discovered this bright structure in the sky, which is called IDEX Ribbon. And so this is the enhanced flux of those energetic neutral atoms, but they come from far away. They come from 100 or 200 astronomical units from the sun, those atoms that IDEX or IMAP IMAP is going to measure from near the Earth. And to really understand the structure, how it formed, and what role these processes play in the global interaction, we have to go there. We have to go where they're born, where they're produced, to measure particles, to measure charged particles, neutral particles, magnetic field. And that will give us that complete picture of processes that produce the ribbon and that form the entire heliosphere.
So it's not a question of it being a requirement to get those results first. Actually, again, it's the question of the synergy and about the about the sum being better than the parts individually. And from my point of view, the best case scenario is that an IMAP or an IMAP2 is up there and working at the L1 point at the Earth all during the time that an interstellar probe would be working for decades. Going on the way out, because that way you get to have the view both from the inside and from the outside at the same time, and that enables you to do a better job of putting the pieces together and really understanding the science and understanding our home.
Thanks. And then second question I got to ask, for this mission, is there going to be a new golden record? Like, what would you want to put that would inspire the broader public?
I'll jump in for a second, and then I think Pontus wants to say something. We have already thought about that, and I'm going to let Pontus speak. As we've been racing to try to get an engineering design that will close, my thought has always been that was a little bit about putting the cart before the horse, as they say, but not necessarily a point of view shared by many of my colleagues. So Pontus, why don't you pick up at that point?
Sure, I'll just pick up a few sentences. Of course, it will not be a golden record, not an analog record. alien civilizations that are smart enough to capture spacecraft, they're smart enough to also read a solid state memory, where you can put I don't know, hundreds of libraries of Alexandria on that little solid state memory. We have talked to what I believe is called the ARC company or foundation that deal with these types of things. The discussions haven't been long, they haven't been deep, but everybody agrees absolutely.
Okay, so we do have a question from the chat. This is, what would the Interstellar Probe have, would there be any differences and similarities between Interstellar Probe and Voyager 1 and Voyager 2?
Okay, Pontus just pointed to me this question. So let me talk about this. So Voyagers 1 and 2 were launched in 1977, and originally they were planetary missions. And of course, they had instruments on board which are tailored to the exploration of those planets. So, and we were lucky that I think in 1991, the Voyager's mission were extended and Voyagers went further to the edge of the heliosphere, but they did not have the the dedicated instrumentation to really understand processes in this region. Although instruments on board the Voyagers are very useful and they gave us a clue of what other important processes are and what kind of, for example, particle species we need to measure on Interstellar Probe. So let me see if okay, anything else you would like to add, Pontus, maybe?
Yeah, you know, I can jump on real quickly here. So we talked a lot about, you know, going out there to measure, but if we jump into physics here and for a second, plasma physics, the really intriguing thing with a heliosphere, with an astrosphere, is that the boundary really starts forming very, very close to the sun. And it's because the penetration of interstellar neutrals, which they don't really care about any of the magnetic fields. And once they get close to the sun, they get ionized, and then they're being picked up by the solar wind. So you can see that the solar wind is sort of seeded by these neutrals and ionized. And once they get out in and meet the interstellar medium, those that were interstellar neutrals before, the so-called pickup ions, they become responsible for the force balance that hold up the entire shell of our heliosphere. It's just an amazing coupling going on. So in that sense, the exploration of our boundary already starts like right after launch. And that's a very important takeaway.
All right, that's great. See, two more hands up. So I'm gonna go to Leo Enright first, and then we'll get back to John.
Okay, thanks, Mike. I don't want to put Ralph McNutt in the spot here, but Ralph, you did mention en passant that you looked at the European options. Now, obviously, the current European vehicles are not capable, but can you talk a little bit about the potential? Because obviously, this is not going to happen just on an American dime. It's going to obviously need other people. And we have, sorry, my heart is still beating rather hard about JWST, but you know, we're about to launch that together. So is that an option?
Oh, well, absolutely. I mean, you know, I think all of us have a lot of European colleagues who we have been talking with a lot. I mean, several of us were actually at the International Astronautical Congress in Dubai that took place at the end of October. And some of our colleagues that we had with us at a special session talking about Interstellar Probe were from Sweden, were from France, were from Russia, were from China. I think we ended up at the special session there, we had about 80 people that had come to Dubai in person to the IAC from literally from around the world. And you know, one of the things that we have been talking a lot about is looking at ways that other countries can contribute. You're right. I mean, it's nice not only to spread the wealth, but also to spread the pain, because these things do cost a lot of money. And you know, it's sort of a question of, well, how do you structure it? I mean, you've got ESA has got their plans and programs in place. The plans and programs for the U.S. with respect to heliophysics are going to be decided by the upcoming decadal. It's always very difficult to figure out how to put these pieces together. You know, for example, I was a project scientist on Messenger, interacted a lot with colleagues on Bepi Colombo. And of course, basically those two missions ended up kind of growing up together. And of course, Bepi Colombo is now on its way out to Mercury to be able to build upon the original Messenger results. We've talked a lot about the fact that there can be contributions from literally all the countries around the world to help be able to provide assets for downlink, to be able to get more data down from the spacecraft, because we're asset starved, you know, on the ground. Once we get to really large distances, you know, the more people that have bit buckets that can be picking up data, the better. With respect to putting instruments on board the spacecraft, there are a lot of people around the world, a lot of people in Europe who are very, very competent and very, very good instrument builders. And, you know, of course, there have been some there have been some rough spots in the overall interactions between the U.S. and ESA along the way. But Ulysses did fly, for example, was one. Its twin, of course, did not, which didn't help things a lot. So these are always difficult. But I think that this is, certainly something that, from the point of view of the decadal, it's something that needs to go through with the process here in the U.S. But we have been trying to be very, very careful about trying to bring in as many people from around the world as possible. And, in talking with them and trying to be frank with them and, saying, we would like to be able to come up with a formula where that everybody can contribute. And of course, I think everybody realizes this is not an easy thing to do. Anybody that's been in this business for a while, but certainly, all comers are welcome. It's a big universe out there, and it's going to take a lot of us to explore it. And Pontus just sees the screen. This is our this was the grouping at the IAC. So this was in Dubai, in the United Arab Emirates at the Interstellar Probe special session back in October. So again, reaching out, we're absolutely reaching out around the world, and anybody that wants to come to the party is more than welcome.
And then there. Okay, thanks, Ralph. And then Jonathan.
Yeah, similar to the golden record question that I wanted to ask about as well. But obviously with the Voyager probe, it's one of the big things the public were interested in was the rendezvous time with other stars. Have you calculated how quickly or what other stars Interstellar Probe might encounter on its way out of the solar system? And separately to that, could someone talk me through the proposed dwarf planet observations? Are there any dwarf planets that are kind of deemed better targets than other ones? And what about the prospects of visiting Planet 9, if it exists? I saw that Konstantin Batygym is one of your collaborators. Has he been asking you about going to Planet 9? Thanks.
Alice, would you like to take some of that about the alternatives for going by dwarf planets?
Sure, I can speak a little bit to what we've been looking at. So we have this baseline heliophysics mission, which Pontus and Elena have done a great job of talking about the kind of science that we'd be looking at with that. But it is 100% true that having a mission out to the interstellar medium is of great interest to both the planetary science and the astrophysics community. So on the planetary science side, we've looked at a number of different candidates for flybys, and I want to say there's something like 10 different candidates listed out in our mission concept report. Candidates like Gong Gong, for example, that one could fly by. This would necessitate a different spacecraft. So those super long antennas that you saw, for example, would need to be short, rigid antennas. but it's totally doable for a similar mass and a similar, yes, Quasar, definitely, is another one that that we've looked at. And then from the astrophysics side, there's a lot of interesting questions regarding the circumsolar dust disk that we have around our sun and what lies beyond it, and being able to take infrared images beyond that dust disk to look at how the galaxy and the universe was kind of made. So there's a lot of cross-divisional science opportunities here beyond the primary heliophysics science that we could accomplish with a relatively similar spacecraft, in fact, and relatively similar instrumentation, with the exception of adding a few imaging cameras.
Could you just describe what you could do on a dwarf planet flyby? Would it be similar to New Horizons?
Very similar, yeah. So the concept of operations that we outline, which is, you know, one example of what one could do in the mission concept report, is very similar to what we did with New Horizons, with both Pluto and Arikoth.
So if you download the massive report, that would be Appendix A for you to look at.
We also have some really great foldouts that I'm sure we can get to you that summarize the baseline mission and then this augmented mission and give you like a really quick look at it. So you could also read 5 pages instead of 500 if that was easier.
Yeah, I was going to bring up that there's an executive summary in that report. There are the foldouts that Alice brought up that be separately, and there's a fact sheet that goes along with that too. And in fact, we've got a few of them sitting in the room next door. But I'm also putting my my email and my cell in the chat. So anybody, again, if we don't have, because we're coming up against it for the hour, and if anyone thinks of questions afterward, if you're not able to join the team after this, and you have something you want to get in touch with the team or anybody else working on Interstellar Probe at APL, give me a call or send me a note, and we can make that happen as well. So I think.
Could you quickly say about encounters with other stars? Has that been calculated? Are there any that would kind of be not within reach, but
they're far? But yeah, please, whoever he's pointing to, I can't put Pontus, you point and I can't see.
Well, let me jump in again for a minute. Yeah, you know, those calculations were done for the Voyager some time ago. We have not delved into looking at that, and you know, again, this report is really capturing the menu. So there aren't any decisions about, well, you know, pick a direction or pick a dwarf planet, or do you want to have a planetary payload? Again, what we've really aimed to do is to really cast a very wide net to come up with what the options look like. I mean, typically, if, you know, let's suppose that this were to go forward within the context of the decadal survey and that there was more interest that the community expressed, and it made sense for NASA to go ahead and take a next step of looking. Typically, what one would do is to put together a science and technology definition team to start taking a look at the menu and deciding what to perhaps actually order for dinner, with the idea that at least we've got a menu and we've got a price tag on each of the entrees, so people would know what that they were getting into. I mean, this has typically been the procedure that's been followed for large strategic missions. Again, we're looking, this would be something on the scale of Parker Solar Probe, and this is exactly the sort of thing, a procedure that was done with Parker in order to come down to making decisions about exactly what should be in a payload and what one should actually do with the mission.
That's cool. Let's see. So looking at the minutes, Leo, why don't you want to bring us home?
Yeah, sorry, just a quick comeback to Ralph, if I may. First of all, if I may say thank you, Mike, and everybody for doing this. It's been very, very interesting. Also, I want to acknowledge that Ralph and the entire messenger team have been extraordinary in their cultivation of young researchers. And I'm thinking here specifically of young Irish researchers who've had their extraordinary opportunities thanks to the messenger program. So I just wanted to put that, as it were, on the record. But Ralph, I was wondering, have you, or do you know of a European rocket that could take this where you want it to go?
We don't know. I don't know of a European rocket right now. The thing that we were talking with some of the people at Arianespace about were potential upper stages, and given what that they've been doing with the propulsion system on the Orion system, and whether some of that might actually feed into what we've currently got as the Centaur upper stage. I mean, as you know, as far as I know right now, again, talking about this is the same class of vehicle as the Saturn V and the Soviet N1. And so right now, you know, what's out there is the SLS. Like I say, notionally, what I know of for the predicted performance for the New Glenn and for Starship. And I believe also that that in China, I think the notional characteristics of the Long March 9, and I've got no clue, you know, how far off of a piece of paper that one has gotten. But again, you know, it's the sort of class of launch vehicle that you would need to be able to take, say, on the order of 40 metric tons to lunar orbit. And again, it takes big launch vehicles, and it takes they're not easy to build, and they're not cheap. And so again, I don't know of anything right now that are in plans with respect to Europe and ESA. On that score, I know that there are certainly, again, these interactions between ESA and the US on the Artemis program. And so you may know something I don't know, and if you do, well, you should tell me.
Okay. So with that, I will thank all of you for calling in and for taking part in this. Then thanks, of course, to the Interstellar team for taking part in this and back and forth. Again, the contact information, my contact information is in the chat. Grab that. Please do go by the Interstellar Probe website, download the report. It's right on the homepage. And if you go through it and you get some of the summaries and see you want more information, we do have some of the graphics. In fact, all the graphics that Alice showed in the presentation to begin with. Those are available as well, including high-def versions of that entire animation sequence. So again, just let me know, and we can get that to you in a reasonable fashion. So if there's anything else, I do see there's one more question here. I think, Ralph, I will answer this the session about this one question here about the sessions. Are there any more Interstellar Probe sessions here at the meeting at AGU, or was that was yesterday, correct?
That was yesterday.
Okay. Yep. So that's what we have on there. So I guess with that, I can hand it over to Lisa too to wrap things up.
Well, I guess let's just say that. So several of us are here on site in, I think it's R05, and so if any of the audience is on site and wants to chat some more, I guess Lisa will tell you how to come find us.
Thanks to our panel for a wonderful conversation. And as I said, we have Pontus, we have Ralph and Elena here in R05. That's just down the hall from the main press room. You are here. You're welcome to come and chat with them. And of course, we have Alice on the line. We can get her back for you. And Mike has given you his contact information for how to get in touch remotely. We'll be back tomorrow at 9 a.m. at the press conference from NOAA on extreme events in 2020. I threw a link in there to the media events for those who are curious about our other media events lined up for the rest of the week. And it's been delightful to have you all here with us. Please come back and see us again tomorrow. Bye, everyone.